Welcome to the second video in our series, A Radical Look at the Mathematics of the COVID-19 Epidemic. I'm Craig Kinghorn, President and CEO of the Strathmore Group. In this video, we explore the mathematics behind the disease process and explain how infectious disease can lead to a pandemic. Don't worry if you weren't a fan of mathematics in school. There won't be any equations and there certainly won't be a test at the end. So just sit back and relax and let's see if we can give you a little better understanding about how all of this works. Thanks for watching. Mark Twain once said, "What gets us into trouble is not what we don't know, it's what we know for sure that just ain't so." In order to see the entire elephant, I need to change the way you think about a few things. First, we need to look at a few key concepts that will help us understand the spread of the COVID-19 virus, as well as show us how to deal with its impact on our society. The first of these concepts requires that we know something about the mathematics of the disease process, and especially the frequency-severity relationship of nonlinearity. Put simply, this just means that, like the blind man holding onto the elephant's tail, when it comes to curves, the overused shibboleth of bending the curve just touches on a tiny part of the entire COVID-19 elephant. To understand the second concept of epidemiologic exponentiation, oddly enough, we have to turn to physics rather than medicine in order to look at chain reactions in critical mass. But let's start with the mathematics of the disease processes. And I promise for those of you who hated math in high school, you won't see any formulas and there won't be any tests afterwards. Now, there aren't very many real laws when it comes to mathematics, but one of the most persistent is the law of unequal distribution. In order to explain it, and the whole concept of nonlinearity, I need to take an indirect approach and talk about something that most of us experienced at one point in our lives, the decision whether to buy a new or a used car. Whether we've actually purchased a new car or not, most of us know that as soon as you drive it off the lot, it's worth significantly less than you paid for it just a few minutes earlier. We also know that for most cars, its value continues to drop every year that you own it. There eventually comes a time when we notice that as our car gets older, the repair bills get bigger and it gets more expensive to maintain. This leaves us with a bit of a quandary. Should we keep the car and pay the increasing maintenance cost, or buy a new car and trade the increasing maintenance cost for a fixed monthly car payment? A few years ago, I ran across the digital data set for automobile price and repair costs from a company called Edmunds, an online resource that helps car shoppers make better buying decisions. The data consisted of thousands upon thousands of seemingly random digital data points. Car A was purchased for $22,000 in 2018, Car B was 5 years old and cost $1,200 to repair and maintain, etc. Page after page after page. Now, to most people, this looked a little like a digital trash can filled with noise. But I realized that this was just like the healthcare data that we use to rate insurance plans, just on a different subject. I thought, what would happen if we applied the same processes and tools on the Edmunds data that we use for our healthcare clients? So, with a little work, this mass of raw data was transformed into a table, and eventually into a chart. Now remember that our original data set was derived from thousands of cars, and for purposes of our analysis, it had to be normed to a constant initial value, which is why the scale is set to 1. The original Edmunds sale price data are shown in red on the histogram, and you can see the dark blue line showing the cost of repair increasing as it moves to the right. What may not be immediately apparent is that both of these values follow their own logarithmic scale. All that means is that sales price values decay or depreciate at a constant rate, while the cost of repair data increases or exponentiates at its own rate. The fun part of this exercise is the optimization curve in the middle, which actually has nothing to do with COVID-19, but it's very important for the original purposes of this chart. If you examine the chart, you can see that your best option is to buy the car after it's had 4 or 5 years of depreciation, while the repair costs still remain very low, and then sell it no more than 4 or 5 years later, before the annual repair costs approach its depreciated value. Hopefully, if you don't learn anything else from this video, at least now you know the most cost-effective way to buy a car. But here's the point of the exercise. Notice that beside every red column is a blue column that represents the calculated value based on the underlying logarithmic depreciation rate, which you see as the dotted blue line. While the red and blue columns are about the same height, they're not exact. That's because real-life data is rough and varies a bit. So even if you've calculated the perfect log, there will always be some variance. But this variance gets smaller as your data set gets bigger. So now that you know about buying cars, I bet you're asking yourself, how does all this relate to COVID-19? They both involve something called nonlinearity, which just describes a relationship that doesn't follow a straight line. I'll explain more about that in just a minute. This principle of nonlinearity was first articulated by Vilfredo Pareto, an Italian mathematician, back in 1896. Most of us have heard a simplified version of Pareto's law of unequal distribution called the 80-20 rule, or the principle of the critical few. At the time, Pareto was studying property distribution and noticed that approximately 80% of the land in Italy was owned by about 20% of the population. He then started looking around at other countries and discovered that while the percentages varied slightly, the general relationship applied regardless of the population, the form of government, or the economic system, and it's still true today. These two charts show income distribution in the United States today. As Pareto would have predicted, the same unequal distribution applies here as well. But Pareto's law of unequal distribution isn't limited to income or wealth or property. It applies to most things that we experience in our daily lives. For example, roughly 80% of our business's profits come from 20% of our clients, and about 80% of our problems come from about 20% of our employees. It also shows that the greatest results can be achieved at the least cost by focusing on the critical inputs that produce most of the outputs. That is, by addressing the roughly 20% that are responsible for most of the problems or give us most of the opportunities. Hence, Pareto's principle of the critical few. This includes the cost of healthcare and even the impact of disease itself. Here are just a few pictures of charts that I pulled off the internet that show these same measures of frequency and severity. The first graph shows the distribution of alcohol consumption. You can see that most Americans drink little or no alcohol at all. On the other hand, those who do consume it in almost reciprocal disproportion. In other words, a few people drink a lot, but most people drink very little, just like Pareto theorized. The next chart, right below it, shows that the frequency of spontaneous miscarriage declines at a smooth logarithmic rate, and over to the right, that breast cancer risk increases exponentially, and below that, as does deaths from lung cancer due to cigarette smoking. And even social pathologies like sexual addiction, whereas the frequency of non-addicts drops, the severity of the remaining few's actions increase. Throughout history, humanity periodically experienced a reassessment of the fundamental aspects of our pre-existing worldview. Whether it's Copernicus placing the sun at the center of our solar system, Gutenberg inventing the printing press, or the discovery of information theory and genetics, sometimes it takes someone pushing the reset button to get us to see what we only thought we knew. Often, this vision is introduced by considering something seemingly unrelated. So, since we're discussing infectious disease, naturally we need to talk a little physics. I recognize that this will sound like a bit of a non sequitur, but to understand how infectious diseases become epidemics, we first have to understand exponentiation, and there are certainly a lot of examples from real life to pick from. We could have looked at the way building fires grow, and if you have a few minutes, I recommend that you Google flashover and check out a few of the videos. But there's really no better example of exponentiation than what happens in an atomic reaction. Let's say that you're a crazy dictator and you want to get rid of your equally crazy neighbor, so you decide to build an atomic bomb. This is the process that's required to create an atomic fission reaction. In its simplified form, this process begins with a single high-speed neutron striking a uranium atom, causing it to split, releasing a tremendous amount of energy along with more neutrons, which then go on to split other uranium atoms until the chain reaction exponentiates. All the atoms are engaged and the bomb blows up. Now, in theory, this is a pretty simple process, but there's a lot more to it than that. In order to get a chain reaction to exponentiate, you need to have a critical mass of fissile material. A critical mass is just the smallest amount of fissile material that's needed for a sustained atomic chain reaction. The amount of uranium you need to reach a critical mass depends on several factors, including the level of enrichment, density, temperature, and reaction efficiency. This last one is usually created by placing a reflector around the fissile material to redirect free neutrons back into the reaction. If you initiate a chain reaction and have achieved critical mass, the reaction will exponentiate and your bomb will explode. If you have too little fissile material, called a subcritical mass, the bomb won't exponentiate and you'll end up with a dud, or perhaps a dirty bomb. So here's where we get to epidemiology and COVID-19. For each of the components that affect exponentiation in an atomic bomb, there's a near-perfect analog in an infectious disease epidemic. For volume of fissile material, the equivalent is population. A larger population, like more mass, makes exponentiation easier. Enrichment equals population condition. An older population, or one that's never been exposed to the infectious disease, like higher enrichment, makes the exponentiation easier. Density equals density. Whether it's atoms or people, the tighter you pack them, the easier it is to exponentiate. Temperature equals level of interactivity. Higher temperature makes atoms move faster and interact more. When people interact more frequently, it's easier for transmission to occur and for the disease to exponentiate. Efficiency equals containment. Weapons designers use neutron shields to feed neutrons back into the reaction. Similarly, constraining people in a bus, a subway car, or a building, like a nursing home, makes transmission much easier and dramatically reduces the number needed for exponentiation. And, like the critical mass of an atomic explosion, each infectious disease has its own critical mass that's based largely on a coefficient of its infection rate, the length of its period of communicability, and its mortality rate. From the perspective of the virus, the infectious disease is more deadly if it's highly communicable, contagious for a long period of time, and not an overly efficient killer. Most importantly, in both dynamic processes, all the factors increase exponentially, but they're not merely cumulative. That is, they don't increase by simply adding to one another. They amplify, meaning that they multiply or leverage each other. This decreases the amount of resources needed to exponentiate, in the case of an atomic reaction, to create a bomb, and in the case of an infectious disease, to create a pandemic. So how big a problem is this? The United States is a large country, but half of the population lives in only a few counties. This map shows just how unevenly the population is distributed. If we were to chart the density of each county and the corresponding relative frequency, we'd encounter our frequency-severity relationship once again. That is, there are a lot of very sparsely populated counties, but only a few very densely populated ones. And looking at just the 100 counties with the largest populations, you can see our Pareto distribution popping up again. And this doesn't even include the other 3,043 other counties or county equivalents that didn't even qualify for the chart. To give you a sense of just how widely divergent this population density is, let's compare three counties: San Diego, California, Hughes, South Dakota, and New York City, New York. While San Diego is the fifth most populous county in the country, it's also very large geographically, so our population density is just a little above average, with a density of just under 800 people per square mile. Hughes, the home of South Dakota's state capital, Pierre, has a very low density of just 22 people per square mile. New York City, on the other hand, has the highest population density of any large county in the country, with almost 28,000 per square mile. And if you want to see real population density, look at the borough of Manhattan, with a population density of almost 72,000 people per square mile. This graphic shows you the change in population density of just the 20 most dense counties in the country, beginning with Cuyahoga, Ohio, which is Cleveland, and ending with Manhattan. But here's the real shocker. This graphic shows the population density of Manhattan, then San Diego, and finally Hughes County, South Dakota. At this point, I might say something about how badly they need social distancing orders in South Dakota, but that would sound just a little bit too snarky. Instead, let's look at the distribution of COVID-19 deaths in the country's 100 most populous counties. Once again, we see our Pareto distribution, but this time New York City accounts for almost 30% of all the COVID deaths in the entire country, and if you add the broader metropolitan area, it's actually over 50%. So this leads to a question that I'm amazed has gotten almost no attention from anyone in the media. Is there a correlation between population density and COVID-19 deaths? And before I show you the next slide, let me just explain a little more about these comparisons. Whenever we want to compare two data sets, we run what's called a correlation study to tell us how well the two associate to each other. This kind of statistical analysis produces something called an R-value. If the correlation is perfect, as would be the case if we were looking at the correlation of pregnancy to genetic females, the R-value would be 1. If the correlation is completely wrong, as would be the case if we were looking at the correlation of pregnancy to genetic males, the R-value would be -1. If there were absolutely no correlation at all, the R-value would be 0. Any R-value below 0.3 is considered weak. Any R-value between 0.3 and 0.7 is considered moderate, and anything over 0.7 is considered strong. And we rarely see studies with an R-value over 0.85. So here you have it, a nearly perfect correlation between population density and COVID-19 deaths. And just for fun, I ran the same figures by state, county, and even city where the data is available, and the results are always the same. This correlation is almost constant. But remember, density is still only one component in determining susceptibility to COVID-19 exponentiation. Let's look at age as another variable. This is a slide from a rating study that I did a few years ago. In this graph, we looked at the distributed health claim cost of an insurance company's population broken down by sex. Aside from confirming that women are about 35% more expensive than men overall, you can see that in unisex rating, men, and especially young men, substantially subsidize everyone else in the pool. But this isn't specifically about healthcare costs. What I'd like you to notice is the shape of the black dotted line, which represents the underlying unisex rate. Here we see the scatter analysis for a rating study for another client. Once again, if you look at the black trend line, you'll see that the slope is almost identical. With the exception of a relatively small tick upwards for newborns and infants, the costs increase at a constant logarithmic rate as members of the population get older. Interestingly, the curve retains its essential shape whether we're considering an age-to-cost relationship or we're looking at a mortality curve. This mortality curve happens to be one from the 1911 to 1917 wave of the Spanish flu and the more severe second wave that took place in 1918, which has received so much attention of late. Another slide that I'd like to spend an hour or so discussing. As you can see from this slide, COVID-19's mortality curve is much simpler and the correlation to age is much stronger. And since there are vastly fewer Americans over 65, 75, or 85, if we adjust to make the death rate a function of the size of the underlying population, the exponential nature of the curve is even more obvious. In other words, the chance of death for anyone under 70 who doesn't have a pre-existing comorbidity is extremely low. And what are COVID-19 comorbidities? Well, first, comorbidity is just a chronic disease or condition that a patient has in addition to being infected with the COVID-19 virus. For example, diabetes, hypertension, and cancer are three comorbidities that have proven to be especially dangerous when paired with COVID-19 infections. The fact that the affected population, the elderly and those with serious comorbidities, is such a narrow segment of the population should present us with an amazing opportunity to combat the disease, but it appears that nearly all the experts have missed it. So let's sum up what we've learned. All disease processes follow similar frequency-severity curves, including COVID-19. A small number of people are seriously impacted, usually about 15%, while most others are unaffected, about 85%. Contagious diseases like COVID-19 exponentiate like atomic bombs, but only when all the necessary conditions have been met. Predictably, COVID-19 has exponentiated in only a handful of metropolitan areas, almost exclusively in New York City and its bedroom communities, both in New York and northern New Jersey. Despite alarmist rhetoric, the necessary conditions for broad geographic exponentiation do not exist in the vast majority of rural, suburban, and metropolitan areas. As a result, geographic exponentiation cannot occur there. Microexponentiation has occurred in hundreds of contained facilities, for example, nursing homes and assisted living facilities, which have been responsible for the majority of serious illnesses and deaths. This brings us to the conclusion of this video. I hope you'll join us for video 3, the next video in this series.